In Math 108, you learned about exponential and logarithmic functions. And if you recall, an exponential function has a constant base, and the variable is in the exponent, as opposed to a power function, which has a variable in the base and a constant exponent. So, for example, let's list some examples of exponential functions. Exponential functions would be like 2 to the x, or you could have like 1.05 to the x, or you could have e to the x, right? All of those have a constant base, and the variable x is in the exponent, as opposed to a power function. Okay, so a power function is like x to the n, right? X to the n, where the n is a constant. So x squared or x to the -5. Those would be power functions. Okay, so Euler's constant e is considered the natural base, and e is just a number. So this e here, right here, this is just a constant, okay, and e is equal to about 2.71828. But it has, it's just like pi. It's an irrational number where the numbers after the decimal place go on forever without repeating. And we like to use a base of e in calculus because e to the x has a very simple derivative. The derivative of e to the x is e to the x. You can't get much simpler than that. So now the inverse of the exponential function is the logarithm. Okay, so if you remember, if we have b to the y equals x, then the log base b of x equals y. Now, with a natural base, if we have e to the y equals x, that means that the natural log of x is equal to y. All right, so see how the input and output switches between the exponential and the logarithmic functions. And the derivative of the natural log of x is just 1 over x. Okay, so we're just going to practice some problems with taking the derivative of functions that involve e to the x and natural log of x. Okay, so this first one, and we're going to remember those rules that we had before with constant multiples of a function and sums and differences of functions as well. So the first example we have here is just f of x is equal to 7e to the x. So the derivative, f prime of x, we're just going to hang on to that constant 7, take the derivative of e to the x, which is e to the x, and then we have minus 4, and remember that the derivative of a constant is 0. So we don't even have to write that. So we're done. The next one, g of x is equal to e to the x over 5. Now we know how to deal with constant multiples of a function, but what happens when we divide a function by a constant? Well, we can always turn division into multiplication because dividing by 5 is the same as multiplying by 1/5. So this is really the same as 1/5 e to the x. Okay? And so now we can take the derivative, g prime of x, and we can just hang on to that 1/5 and then take the derivative of e to the x, which is e to the x. So the derivative of e to the x over 5 is essentially e to the x over 5, because we could rewrite this as e to the x over 5. All right, so this next one's a little more challenging. We have e to the x minus 3. So that whole x minus 3 is in the exponent. Now we have to use the properties of exponents to rewrite this. And if you recall, we can rewrite this as e to the x over e cubed, right? Because when you have a quotient with the same base, you can subtract the exponents. All right, so if we have a difference in the exponent, we can go the other way and write it as a quotient. All right, now we could also write this as e to the minus 3 times e to the x, either way. Okay, but now you can see that this is just a constant, right? This is a constant. And we can take the derivative now of this function, and we're going to hang on to that e to the minus 3 and take the derivative of e to the x, which is e to the x. So there we go. it's the same thing again. And we could rewrite this if we want to back. We can take we know that if we have the product of two exponentials with the same base, we can add the exponents, right? And so we could rewrite this as e to the x minus 3 if we want to. All right. Look at this next one. We have e to the x plus 5 all over 5. Okay, so we need to rewrite this. So I'm just going to divide each term in the numerator by 5, or you can think of it as multiplying by 1/5. So I can just rewrite this as 1/5 e to the x plus 1/5 e to the 5, right? You're sort of distributing that. Dividing by 5 is the same as multiplying by 1/5, and then you're just distributing the 1/5. You can think of it that way. All right, so now we're ready to take the derivative. The derivative, I'll write it, dy over dx is equal to 1/5 e to the x, and this term here doesn't have a variable in it, so it's just a constant. This whole thing is a constant. That's a constant, and you take the derivative of a constant, and it's 0. So I'm not even going to write it down. All right, let's look at this next one. So now we have a log in this one, but this, just remember, if you don't see a variable, it's a constant. So this right here is a constant. Now the e, it looks like a letter, but it's not a variable. It's a constant. It's Euler's constant. And so that whole square root of e is also a constant. So we can take the derivative of this function, and the derivative of constant is 0. The derivative of the natural log of x is just 1 over x. So that's our derivative. All right, now this one we need to rewrite as well. We have both an exponential and a log function in this. So let's rewrite the square root as a 1/2 power, right? That's the same thing. So I have e to the 2x, all of that to the 1/2 power, right? And then minus 5 ln of x. All right, now when I take a power to a power, I multiply the powers. So if I take 2x times 1/2, I'm just going to get e to the x. All right, so now I'm ready to take the derivative. I'm going to call it dy over dx, and I get e to the x. I'm going to hang on to that constant and then multiply it times 1 over x. Okay, so 5 times 1 over x is the same as 5 over x, so I could write it as this second term as 5 over x if I wanted to. But this is fine the way it is. All right, got a couple more here. So let's see, we got to simplify this. We have the same base. Both of the numerator and the denominator have a base of e, so we can subtract the exponents, right? So we're going to get 2x minus x, which we can simplify down to just x, e to the x. All right, now that's easy. I'm going to take the derivative now, dr dx, we'll call it, and it's just going to be e to the x. All right, now we have to use the properties of logarithms on this next one. We have the natural log of 10 times x. Okay, now we know the derivative of the natural log of x, but not necessarily 10x. So we have to break this apart. When you take the log of a product, you can break it up into the sum of logs. So we're going to rewrite this as the natural log of 10 plus the natural log of x. All right. Now, again, so natural log of 10, that's something I could just put in my calculator and get a number, right? So that's a constant. That's a constant. And now if we want to take the derivative, we get the derivative of natural log of 10 is just 0, and then the natural log of the derivative of natural log of x is 1 over x. And we're done. All right. So I'll see you, I guess that's the last video, so I'll see you in class.